Okay, so hello everyone and welcome to the week 6 material selection and design topic. So the topics number 6 is going to be about design consideration, mainly about the corrosion and the degradation. So I think that you all know about the corrosion. Sounds like what you have here is rust. The continuous solid rust is going to cause the corrosion. So first we're going to talk about the environmental impacts on the materials, where to some extent some of the materials interact with their environment, and this can take many forms such as the chemical, like for example the oxidation, or physical, which is going to be the erosion. Temperature, pressure, and environmental aspects like the humidity or the UV exposure are also going to be an influential. As a result of the environmental interaction, materials generally tend to lose performance, and they tend to weak or become less attractive. And they can also lose electrical or thermal properties. As a design engineer, it is going to be important that environmental factors affecting the selected materials are closely considered. So consideration, the three broad materials families, metals, ceramics, and the polymers. The polymetals usually going to be tend to oxidize, and of course this will cause the corrode or dissolve. For the ceramics, they tend to be a very stable but can be dissolved. For the polymers, they tend to dissolve or swell, and they are also susceptible to heat and radiation. So for the corrosion in the metal, as you can see actually from the photo I added here, these are some examples of the corrosion we can have due to the oxidation. So according to the Callicet 2020, corrosion is defined as the destructive and the unintentional attack on the metals. It is electrochemical and orderly begins at the surface. Corrosion of the metals is a major economic issue. Managing the corrosions account for about 50% of a developed nation's income. Corrosion is frequently encountered as a rust, which is a corrosion product of the iron-based alloys, like the steel. The corrosion product can also be advantageous for example, for the aluminum can. So the aluminum can usually not going to be corroded. The electrochemistry basics for the corrosion in general. An electrochemical process is a type of the chemical process that requires the transfers of the electrons between the reactant and the products. So the electrochemical reaction consists of two complementary processes. First, the oxidation process, and the second one is going to be the reduction process. An electrochemical reaction cannot proceed unless both oxidation and the reduction take place at the same time. So we start with the oxidation. So focusing only on the metals, oxidation involves the loss of the valence electron, which is the E that we can see in the equation here. Let me bring my laser pointer. Okay, so the E here is an electron, which is going to be usually lost if we're going to put the negative sign on it, from a metal atom N to yield a metallic ion, which we note as the M up to power N plus, and a packet of electrons. So in this equation, you can see that the metal, if it's going to lose the number of the ions, the oxidation is going to be to the power of the number of the ions we're going to lose. An example we have here that the equation telling me that the ferrous, which is the iron, is going to add two oxidation ions by losing two electrons. Okay, so it represents the oxidation of the iron atom, the Fe, of the iron ion, Fe up to power 2 plus, where the two electrons, the 2e negative, were lost or released during the process. The same thing we can see here for the aluminium. It's going to lose 3 ions, and thus it's going to have the oxidation, the oxidation up to power 3. So oxidation specifically refers to the increase of in the oxidation state of this species. Looking at the example for the iron, the Fe has an initial oxidation state of 0, and after reacting, the oxidation state will increase to 2 plus. The oxidation takes place at the anode, because we have cathode and we have anode. It's going to take place on the anode that's going to lose the ions instead of getting them. So for the completion of the electrochemical reaction, the electrons generated during the oxidation must be also consumed by the reduction process that takes place at the same time. So the reduction requires that the oxidation state of the species is going to be reduced. If the environment is going to be highly acidic, reduction could involve the reduction of the hydrogen ions to yield the hydrogen gas. And the example we can see here that we're going to have 2H up to power plus the 2 ions that we're going to get from the freon, for example, is going to cause the hydrogen to be released. So it's going to be reduction, health equation, or the cathodic reaction. So if the environment is acidic but also contain the oxygen, then the alternative reduction reaction may be proceed, such as that the oxygen, 2 atoms of the oxygen plus 4 of the hydrogen plus 4 ions, we're going to release the H2O, which is made again to be a water. That's what you can actually see in this diagram for different materials. So under natural or basic aqueous environments, reduction could also be proceed as the equation to be written as 4OH. Okay, 4OH. That's when you get to have a water instead of the hydrogen. Now reduction takes place at the cathode. You remember that the oxidation at the anode, but this will be at the cathode. Reduction can also undo the oxidation of the metals. So multiple reduction processes can occur simultaneously, and they can also be proceeds in a stepwise sequence. The critical requirement is that whatever the reaction process occurs, the reduction can only consume the electrons generated from the simultaneous oxidation process. A simple example is, we're going to have the zinc. After reaction, we're going to have the zinc oxidized to 2 atoms and losing 2 ions. If I'm going to have the 2H plus 2E, and I'm going to have the H2 as a release. That's reduction health equation. The Zn plus the 2H plus, we're going to have after reaction that the Zn2, the oxides of the zinc, plus the H2 to be released. That's the complete reaction process. So under acidic conditions, the zinc corrodes to a Zn plus, and the hydrogen gas is going to be produced. And yes, if you're asking, this is one of the ways to produce the hydrogen in the lab. So the tendency of the metals to oxidize varies from one metal to another. So for example, we have here 3 oxidation relationships as we given here. First one is going to be for the ferrous or the iron. That's in the image for the left photo. The middle one is going to be the platinum, and the last one is going to be the AU, which is the gold. So you can see that the equation shown here that, okay, now for the ferrous is going to be ferrous oxidized to raising 2 electrons or ions. Same thing will be having for the platinum, and the same thing will be here by releasing 3 ions in the case of the gold. So the question is, are platinum and gold equally susceptible to corrosion as the iron? I mean, if you're going to make a very short research, you will find that the answer is, well, no. The platinum and the gold are significantly more resistant to corrosion than the iron, and they are also classified as noble metals and are highly unreactive. In the case of how we can find the tendency of the metal to oxidize, simply check the electrochemical series or the activity series, which is going to give you a list of all the uh, tendency to corrode for different metals. So we need to consider the electrode potential. So if you're going to consider the oxidation reactions examples, again with the electrode potential included, we'll find that the oxidation of the freon is going to be happen with releasing 0.44 volt only. While in the case of the platinum is going to be minus 1.2 volts, and the case of the gold is going to be 1.42 volts. So as seen, the oxidation of the iron will yield a positive voltage, whereas the oxidation of platinum and the gold will yield a negative voltage. This means that the iron can oxidize spontaneously while the platinum and the gold cannot. So the NHE standard stands for the normal hydrogen electrode, which is an electrochemical reference potential, specifically that the 2H plus 2 ions is going to cause the H2 to be released, and this will have zero voltage potential by definition. So while it's beyond the scope of this subject, all the potentials are going to be quoted under the standard conditions, and real conditions can be very different, but that is going to be a domain of the electrochemistry professionals. So what will happen if we combine the iron with the platinum to form the electrochemical couples? So the process, as you remember, that considering that the respective health reactions for each one, and can see the respective tendencies to oxidize are going to be a very different. The iron can be spontaneously oxidized, whereas the platinum will strongly resist the oxidation. So again, to combine these two health reactions, I will get that the freon plus the platinum up to power 2 is going to be freon up to power 2 plus the platinum as a metal. So practically, this means that any oxidized platinum will drive towards the metallic platinum at the expenses of the metallic iron, which is going to change to an oxidized iron. So realistically, that the amount of the platinum oxidized at the surface of the piece of the platinum will be very low, so that induce the oxidation of the freon will also be low. Remember that the reduction must always be equal to the oxidation. So the table of the standard reduction potentials is given here, and you can see what will be the electrode reactions for different metals, and what will be the standard electrode potential voltage in volt. So you can see that for the starting from the freon and above here, we're going to have the increasingly inert, which is going to be a cathode, and after the zinc, we're going to have the increasingly active, which is going to be the anodic materials, and in between, we're going to have the values. So what do we have here? Yeah, well, that's it. That's the only thing I want to talk about this one. So written as a reduction reactions, increasing tendency to reduce goes up of the table, and increased tendency to oxidize will go down of the table. If the A and B are going to be coupled, and the A is going to be ranked higher than the B, then the A will reduce and the B will be oxidized, which is going to be a corrode. So once again, when we say ranked higher, that means going to be at this spot, and we saw an example for that for the platinum and the freon. So if the A and the B are going to be coupled once again, and the A was something like the platinum was going to be a higher in the table here, and the B is lower, and simply the B will be oxidized like what we had in the example of the freon earlier. Consider that couple of the freon and the zinc, the Fe is above the Zn, and the Fe has a stronger tendency to reduce. So when the coupled Zn will oxidize and the Fe will be reduced, and that's what we call the process of the galvanized steel as an example. Consider that the Cu, which is the copper with the Fe, the Cu is above the Fe in this table, okay, and sorry, above the S, so the Cu will be reduced and the Fe will be oxidized. But don't use, that's why we don't use the iron nails to secure a cover sheet, because the freon will be simply oxidized and got filled. Now we continue with that. The galvanic seals of the seawater at 25 degrees, we're going to have resistance to corrosion decrease down the list, and the active or the passive refers to the state of the surface with the respect to the presence of the passivation layer. So the passivity itself is under certain environmental conditions, a metal may form a thin oxidized layer at the surface that provide a corrosion resistance. An example for that are the stainless steel and the aluminium. And actually, if you see some videos for the aluminium casting, you will find that there will be a thin layer of the oxidation on the top surface of the molten metal. They try not to sacrifice because this will be a resistance for the corrosion. Also, if you're going to have any aluminium surface around you later, just try to scratch the top and you will find that the surface beneath is going to be more shiny in color. That's mean that the top one was having a layer of the oxidation that protecting the other surface, and the new surface will be soon to be oxidized. So the passivity, once again, under certain environmental condition, metal may form a thin oxidized layer at the surface that provide the corrosion resistance. So let's have a look here about the chrome oxide layer protecting the stainless steel. We have the chrome oxide layer damaged by the machining process, so it's going to create an oxidation layer to reform it and start the protection once again. Okay, so to be passivating, the layer must be continuous and will adhere to prevent the ongoing oxidation of the material. The pacification can serve to be a self-healing features of some of the metals. Now we go into the environmental effect. You all know that actually when we are going to have higher humidity, we're going to have higher corrosivity. So increased temperature generally tends to increase corrosion rate because the heat is a booster of the chemical reactions. Increased fluid velocity tends to increase the corrosion rates. Increased concentration of the corrosive species tends to increase the corrosion rate. And the cold working tends to promote the corrosion due to the creation of the anodic sites. So again, if I get to repeat that, just to make you remember what we said here. The higher the temperature is, the higher the corrosion is. The higher the fluid velocity tends, the higher the increase in corrosion rates. Increased concentration of the corrosive species tend to increase the corrosion rates. Cold working will tend to promote the corrosion due to the creation of the anodic sites. So the corrosion of the metals can be classified according to eight general types: uniform attack, galvanic corrosion, the crevice corrosion, the pitting, the intergranular corrosion, the selective leaching, the erosion corrosion, and the stress corrosion. So we're going to go briefly about it. So the first type of the corrosion is uniform attack, which is an electrochemical corrosion that occurs with roughly uniform intensity across the exposed surface. It tends to leave the deposit or the layer of the corrosion products, and this form of the corrosion is easily predicted and designed for. An example for that includes the rusting of the steel and the transitioning of the silverware. So the second type is the galvanic corrosion, which is an electrochemical corrosion that occurs when two metals or alloys are going to be electrically coupled in the presence of the electrolyte. The galvanic corrosion is predicted by a table such as the standard reduction potential or the galvanic series. The rate of the corrosion depends upon the relative exposure of the cathode and the anode surfaces. A small anode will occur rapidly if they couple to a large cathode. So the galvanic corrosion can be reduced by first avoiding the coupling of the dissimilar metals or minimizing the dissimilarity. Also ensure that the anode area is going to be as large as possible relative to the cathode. Third, electrically insulate the metals if possible. And finally, connect the third metal that can be conductively replaced over the time, which is mainly going to be something like a sacrificial anode or the cathodic protection. The example includes the rusting of the steel pipes if connected to a copper pipes, as may be this case of the domestic hot water system. The steel screw securing the brass fixture and the marine setting would also going to be susceptible to corrosion. The crevice corrosion is a electrochemical corrosion that occurs due to the formation of the concentration gradients within the electrolyte, and this will leading to the formation of the dissimilar regions along the single metal piece. In locations where an electrolyte can become stagnant, for example, in the crevices under the washers or the layers of the dirt and extra. The region of the depleted oxygen can form, and this will lead to the build-up of the species that can attack any passivations layers that are going to be present and lead to the dissolution of the metals. Crevice corrosion can be avoided by designing for the elimination of the tight joints. For example, if you're going to have the welding and you're going to have this area to be filled with the waters, for example, or the humidity. Form of the corrosion is the pitting and is a high localized form of the corrosion whereby the small pits or holes form in the surface of the affected metal. The pitting occurs similarly to the crevice corrosion, whereby the concentration gradients become established between the bottom of the pit and the surface of the metal. Mainly is going to be initiated as scratches or small surface defects, and this can be proceeds without detection until the failure will occur. Highly polished surfaces will tend to resistant to a corrosion from the pitting. The intergranular corrosion occurs along the grain boundaries for some of the metals and alloys under specific circumstances. The result is a disintegration of the materials over the time. The circumstances of the intergranular corrosion are specific to the metal or alloy concerned but may involve also the formation of the precipitate at the grain boundaries under the action of the sufficient temperature. Being derived from the grain itself, these precipitates may leave the region close to the grain boundaries depleted in a particular element. The rendering it and related to corrosive attack. The avoiding of the intergranular corrosive involve first the managing of the heat treatment or thermal history of the suspectable materials to avoid the grain boundary precipitate. Second, managing the composition of the alloy to minimize the driving force for the precipitation. And third, managing for the compositions so that the corrosion favorable precipitates form. An example is going to be stainless steel, which will form the chromium 23 carbon 6 particular at the grain boundaries if exposed to temperatures between the 500 degree and 800 degree for a sufficient time. The welding can also lead to the anterior granule corrosion. The other form is selective leaching, and selective leaching occurs when the one element is going to be preferentially removed from an alloy due to corrosion process. So an example is going to be a brass which can become preferentially depleted in zinc and leaving a region of the copper that lack for the mechanical properties expected of the brass. Now we have the case of the erosion corrosion, and this may again to have a mechanical abrasion at the same time. So it combines the chemical attack and the mechanical abrasion at the same time. So you can see from the photo here that the development of the turbulences will cause to the eroding of the materials or eating all the materials due to the mechanical movement. So most of the metals and alloy are going to be susceptible, especially for if the passivation layers cannot be maintained. This mode of the corrosion is favored by increased fluid velocity as well as the presence of the bubbles or the particles. Location of the altered fluid flow, such as the joints, the bands, or the changes in the cross sections are especially damaging. In addition, the erosion corrosion must also be considered in the design of the propeller and turbines. A characteristic of the erosion corrosion is going to be the presence of the wave-like formations and on the material surfaces. Now, the other type is going to be the stress corrosion, what we call the stress corrosion cracking, which is a result of the combination of the tensile stress and the corrosive environment. The propagation of the small cracks due to the applied or residual stress is promoted by the corrosive environment. And this will lead to the failure that is most going to be a characteristic of the brittle failure, even in ductile materials. The combination of the stress and the corrosion also means that the crack propagation can proceed at reduced stress. Reducing the applied stress or the residual stress via the annealing can assist with the reducing of stress corrosion. Now, the hydrogen embrittlement. The hydrogen embrittlement is a phenomenon whereby the ductility and the tensile strength of certain metals and alloys is going to be significantly reduced due to the penetration of the atomic hydrogen. In similarity to stress corrosion, the hydrogen embrittlement leads to the brittle failure and can occur when the atomic hydrogen is going to be interstitially present in the materials at a level of several ppm. For hydrogen embrittlement to occur, hydrogen must be present, and it must be possible for the molecular hydrogen to form an atomic hydrogen. This is possible in humid condition at a high temperature or in the presence of the hydrogen sulfide or the H2S. Such as circumstances are wide-ranging. The high-strength steel are particularly susceptible, and the FCC alloys tends to be resistant. In hydrogen embrittlement is going to be if hydrogen embrittlement is anticipated, then the annealing treatment may be applied to assist with the removal of the interstitial hydrogen prior to the application. So we know that actually the oxidization will form a scale. So the while we have considered a metallic corrosion in terms of the electrochemical reactions, where an electrolyte is going to be present, corrosion can also take place in the absence of the electrolyte, i.e. in the form of the atmosphere. So the oxidation of the metal can be described as the M plus half of the oxygen atom will going to have the MO. So this also going to be consists of two half reactions. The first one is going to be that the M is going to be M up to power 2, which is going to be oxidized by two atoms while losing two ions. So in the case we're going to add half of the oxygen 2 plus the two ions to be removed, we're going to have the O2, which is the reduction half of the oxygen atom. So in this form of the corrosion is called the scaling, transitioning, or the dry corrosions. The result is going to be the formation of the layer of the metal oxide and the surface of the metal. While the scale layer can start easily and initially grows rapidly, over the time the rate of the growth becomes dependent on first the M2 forms of the metal diffusing to the surface, and the electrons diffusing to the surface, and the O2 diffusing to the metal scale interface. So while the migrations of the electrons is going to be typically swift, unless the oxide scale is going to be electrically insulating and independent of the temperature, the diffusion of the ions is going to be relatively low and highly temperature dependent. Hence, a point is going to be reached where continued scale growth is going to be effectively stopped unless the temperature is going to be markedly increased. However, once this point is going to be reached, the metal may be protected from the further oxidation due to the passivation. The oxide scale is a different compound of the metal. So it may or may not adhere to the metal surface, as can be also solid or porous. For the oxide scale to be protective, it must continuously cover the metal. So the Pilling-Bedworth ratio, or the PB ratio, is a convenient measure for the predicting whether the growing oxide scale will provide an oxidation protection to the metal or not. The PB ratio essentially compares for the density of the metal oxide scale to density of the underlying metal. If they are going to be vastly different, protection does not occur. So the Pilling-Bedworth ratio is going to be the AMO multiplied by the rho M divided by the AM multiplied by the rho MO, where the AM and the AMO are going to be the atomic mass of the metal, the molecular mass of the metal oxide, and the rho M and the rho MO are going to be density of the metal and density of the metal oxide. When the PB ratio is going to be less than 1, then that means the scale will tend to be a porous, which is mainly going to be underproductive. If it's going to be more than 2 to 3, then the scale growth with the high compressive stress is going to be susceptible of the flaking off, which is going to be once again unproductive. If it's going to be within the range of 1 to 2, that means it's going to be more than 1 but less than 2, then the scale adheres strongly, which is going to be a protective layer. So the Pilling-Bedworth ratio table for different materials, as you can see here, for the aluminium, we're going to have the aluminium oxide PB ratio should be within the range of 1.29. If I can talk about, for example, the AG here, okay, so the PB ratio should be 1.61. So you can see that actually in some of the ratio we're going to have for the protective should be, we said, more than 1 but less than 2. But here we have 2.1. If we're going to talk about the ratio here, we can have more than 1, okay, and more than 2. Well, actually, these are not protective, but we have the range of 1 to 2 still going to be unprotective, like what you have in the case of titanium or the AG. Now, corrosion of the ceramics, which we said also is going to be presented. So the ceramic most frequently consists of the metallic oxides, the nitrides, or the carbides, as well as many other, and it's also going to be thought of as already of the corroded state. Hence, in general, most of the ceramic processes, a high level of the corrosion resistance. On the other hand, the ceramics are often going to be exposed by the aggressive environments to elevated temperatures. Under such condition of the oxidization is not so much as an issue as a potential for the dissolution or the formation of the unfavorable phases. So a critical aspects considered in the time of the exposure is compared to the metals. Ceramics can typically endure much longer duration on the corrosive situation. Now we can have a degradation in the polymers. So unlike the metals whose the corrosion process largely going to involve the electrochemical processes, the polymers suffer for the degradations due to the environmental interactions that are going to be largely physical or chemical in nature. The degradations of the polymers occurs at several types, but the exact mechanisms of each are going to be complicated by the wide variety of the polymers. The types of the polymetric degradations are the swelling and the dissolutions, and the covalent bonds ruptures, and the weathering. The example will include that the polyethylene will become brittle if exposed to an oxygen at high temperature. Also, the polyvinyl chloride will become discolored at high temperature but maintain mechanical properties. The swelling and the dissolution. The swelling and dissolution frequently occurs when the polymers are going to be exposed to a liquid, and the swelling is going to be the process whereby the polymers absorb some of the liquid. Relatively a small molecular size of the liquid species can be fit between the large micromolecules of the polymers, and over the time will push them apart. So aside from the polymer increasing in volume, the separation of the molecules reduces secondary bonding, and this will leading to the weakened material. Dissolution is going to be similar, except that the macromolecules of the polymers are going to be sufficiently separated for the polymer to dissolve altogether. Hence, the swelling can be thought of as a partial dissolution of the polymer. The tendency of the polymer to swell or dissolve is going to be favored by the liquids that are similar in structure to the similar hydrocarbons fluids. They are fine if exposed to the water. In general, the swelling and the dissolution is favored by first the increased temperature, second the decreased molecular weight, third the decreased cross-linking, and finally the decreased crystallinity. So again, we can have a table for different types of the polymers, and we can see here the effects of the oxidizing acids, the aqueous salt solutions, the aqueous alkalines, and the polar solvents, and the nanopolar solvents. So we can see here about the resistance to the degradation by various environments for the selected plastic materials. Okay, now this is another table, resistance to degradation by various environmental for selected elastomers materials. So of course you know the difference between the elastomers and the polymers. The bond rupture is another degradation we have in the polymers, where the rupture of the bonds among the individual molecular chains that comprise the polymers as a significant impact upon the properties accepted. In the particular, the sections of the chain reduce the effective molecular weight of the effective polymer, which is going to be general determinants of the degraded performance. So the bond rupture can occur in several ways, like the radiation effects, where radiation with sufficiently energy, like the electron beams, the X-ray, UV lights, and extra, can penetrate the polymers and interacted with the constituted atoms and their electrons. Specifically, the radiation can remove the electrons from the atoms, resulting in the broken bonds. This can lead to the rearrangement of the atoms at the affected location, and typically will leading to the increased brittleness and the discolorations. The most common radiation source of the UV light is going to be the sunlight. It is also possible to use radiation to induce the cross-linking in the specific cases, and this can lead to the desirable increase in the toughness. So the other two effects on the bond rupture are going to be the chemical reaction effect, where the chain session can be promoted by the presence of the oxygen, the ozone, and the other chemicals. The presence of the double bonds in the molecular chain are preferred sites for such bond ruptures. So the surface of the polymers can become covered with a protective oxide layer, but upon the application of the stress, this layer will easily crack and degradation continuous. So the use of these stabilizers can assist with the preventing of the degradation by the ozone of the oxygen, and the stabilizers essentially going to perform as a sacrificially to protect the polymers overall. Now we come to the thermal effect. So when subjected to a high temperature, polymers can decompose, and thermal resistance is going to be attributed to a high bonds energies. Specifically, more thermal energy required for the bond ruptures, and the bond energy CF bonds will exceed the CH bonds, which also going to be exceeding the CL bonds. Hence, the fluorocarbon polymers exhibit a higher temperature stability than the chlorocarbon polymers. So finally, the weathering is another reason or effects for the degradation of the polymers. So many polymers are applied to situations where they are going to be exposed to humidity, sunlight, and related outdoor influences. The degradation of the polymers is thus going to be known as the weathering, and involved in the combined effects of the oxygen, the UV, temperature, and the water. As per thermal resistance, the fluorocarbon polymers display a high resistance to weathering, whereas the chlorocarbon polymers readily to be degrade. So a very important reading is going to be the material science and engineering. I know maybe you don't like that because something like more chemistry and you don't like the chemistry most of the cases, but it's going to be nice if you're going to have a look for the chapter 17 of this book. So thank you very much for your listening, and I hope we're going to have more discussion about this video in the lab, in the class.